today as yesterday. It was a little slick, but not as bad. What kind of questions off of limits 4.2 could I help you with? You just got to and you're like, uh-oh. Good on limits 4.2? Hey there. You had the homework from yesterday, right? We worked that together? Yeah. Cool. All right. Any questions? We feel good? Happy about it? Okay, so just a couple of things. So there are times on limits you can directly plug in the number that's given. Even if it says, something like this. This just means I'm going to plug in 2. Okay, it doesn't matter if it's coming from the negative side or the positive side. If it was like something like this, it's just going to directly plug in, so you'd get 9. The only time that you might have to do other things is you might have something like this. They might give you this, and they have x squared minus 4 over x minus 2 on bottom. If you directly plug into this, it's going to give you an undefined thing. So then you have to recognize that I have difference of 2 squares on top. Those cancel out. Once those cancel out, then you're doing the same problem, but you're plugging into x plus 2, and then that would give me an answer 4. But then there's the other thing that if it didn't factor out and you still having to plug it in and the denominator becomes equal to 0, that's when you might want to take a look at Desmos and take a look at what it's doing. Now, if your graph did something like this, and this is basically the value you're looking for, what can you tell me about the limit if that pink line was the limit we wanted to put in? What can you tell me about the limit? Is it positive infinity? Is it negative infinity? Is it both? Is it does not exist? What do you think? So the answer is, if I'm coming this way, I get to positive infinity. If I come this way, I get to negative infinity. Being these are 2 different locations, this would mean that if this pink line, which is just a number, does not exist. Okay? But then there's other times when you look at a limit, especially if you look on your graphs, and you might have some graph that does, all kinds of fun things. So something like that, and I'm just arbitrary. If you had a limit as x approaches infinity, that means I'm following this along. Hey, cool. That just basically means you have to figure out what's the horizontal line that I'm approaching on that line. Sit at that comfy chair right at the desk. There you go. Thank you. Yes, sir. So those are just a few things, and Desmos is going to help you out. The thing what you have to realize about Desmos is Desmos usually takes a decimal out 3 spots. Okay? It's just that's their operating system. It doesn't mean that, if you went way out to, you plugged like 100 million in or something like that, that it gets to exactly that. It's approaching it. So that's what we're looking at with that. So now we are on the page of our book that says derivative notes. Derivative notes. Okay. So a really good basic definition of a derivative is this is going to allow you to find a number or an equation that if you plug an x value in, you could find something called the instantaneous slope. So let's back up a little bit and think about just graphing a line, okay? So if I had some xy axis, and we're going back to Algebra 1, this line has a slope. And we know the slope is referred to as the letter m, okay? Now, something that you would know about a straight line, especially in that case, is the slope stays constant no matter where you are on the line. Does that make sense? So straight lines have a constant slope. Where things get goofy is, let's say I had something like this. Okay? So as I go along this line, if I were to take a line, do you remember the term a tangent line? I'm not talking tangent where you're talking about a triangle where it's the opposite over the adjacent. I'm talking tangent is a straight line that kisses the line once. Okay? So a tangent line woo, that came from the toes. All right. A tangent line, I want that one. If I were to take a whole bunch of tangent lines, meaning it's touching my graph in exactly one spot, that straight line is called a tangent line. A tangent line touches a graph once. A secant line goes right through a line or a graph twice, but a tangent line touches a line once. And as we can see, these black straight lines, the slope of the straight line is changing. It actually gets to a point where you have a slope of 0, and then you have a slope that starts going down the other way. So you can have positive slopes, negative slopes, you can have slopes that are 0, and vertical lines are slopes that are undefined. So the term derivative is something that will allow us to figure out some sort of equation that will be tangent to our graph. And then if we have a value for that, we can then take that value and plug it in and find the instantaneous slope of the tangent equation to our graph. Does that make sense? So I'm trying to, so let's just say we have some sort of graph that does this. And I wanted to find this line. This is a tangent line. It touches graph one time. So because it's a tangent line, the term line is the important part here. Line is y equals mx plus b. That's just our standard form. Yes, there's other forms of lines, but this means I can find the slope. So if I know a value, I can plug it in and find the slope at exactly any location along that line. This tangent line changes as we go right or left on the graph. In fact, if we come here, would you feel comfortable that the first tangent line has a very different slope than the second tangent line? Okay, meaning it touches it once. Okay, so the slope to this would be a positive slope. The slope to this would be a negative slope. Okay, if it's as you go to the right going up, it's positive slope. As I'm going to the right and it's going down, it's a negative slope. Okay, so the derivative has all of these different samples, rules, things like that. But what we're going to do is we're going to talk about how to just do the first derivative. And there is an equation that is given. I just want to see where it's at. Have it right off So it's going to be a little different. Okay, so then we were talking about limits. Limits is as we're approaching something. Limits then goes into a thing that starts bleeding into something called a derivative. So if you see something like this, d dx, this means you're doing the first derivative with respect to x. Okay? And I know that it's a way different thing than you've probably ever heard. If you've never taken pre-calc, you've probably never heard the term derivative. Okay? I'm not going to go into all the fundamentals of a derivative, but what I'm going to do is I'm going to show you an example. You don't have to have this example written, but let's say I had an example of y equals 3x to the fifth plus 2x minus 7. If I was to do the derivative, I would have dy equals 15x to the fourth dx plus 2 dx. If I were to divide everything by dx, I'd wind up getting dy over dx, which means I'm taking the derivative of something both x and y, and my answer to this would be this. Okay? Now, that doesn't mean too much to you right now. That's just how you take the derivative. I haven't shown you how to take the derivative. There is a long, drawn-out process to do the derivative, or there's the shortcut. Okay, the shortcut for us is going to work every time. The long, drawn-out method is you plug x plus h in, you subtract into the function, you subtract the function, you divide it by h, and then it would come out to a similar type of thing. Okay, that's a long drawn-out process. That's something that if you are in pre-calculus, whether you take pre-calculus next year, if you decide in college you want pre-calculus, they're going to go with the long drawn-out way, but then the shortcut takes place really easily. So if I have the derivative of a constant, and the constant is a number only, it'll be equal to 0. So what would d over dx of 1 be equal to? 0. Okay? So that's kind of, and they say, yeah, power rules. There's different rules that take place, and it has to do with how big and complex your stuff is. Power rule, for the most part, we're going to deal with. I don't think we're going to get to the chain rule. We won't get the quotient rule. The sum rule and the power rule are very similar to each other. Okay? So that's the first thing to know, is if I have the derivative of a number only, the derivative of a number only is going to have an answer of 0. So it doesn't matter what this number is. It can be anything beyond 1. It comes out to an answer of 0. Okay? But then they give us d dx of x. Okay? So a few things that we need to know about this. Is x raised to the first power if it's just sitting there as x? Make sense? All right, this is how you're going to do the derivative. The exponent comes down front, and then I subtract 1 from the exponent. 1 minus 1 becomes 0. What's x raised to the 0 power? Anyone know? 1. So this becomes 1 times 1, which is just 1. So the derivative of x is just 1. So basically what you want to do is you take whatever the exponent is, that exponent comes down front, and then we reduce the exponent by 1. Okay? So let's say I have d dx of x squared. Let's use the same thought process. I'm going to bring the exponent down front, so I get 2x, and I subtract 1 from 2, and I get 1. So the derivative of x squared is just 2x. Okay? Anyone want to take a shot at d dx of x to the third? 3x squared. 3x squared, you got it. And then we have d dx of x raised to the n. So that's n times x raised to the n minus 1. This right here is the shortcut of doing a derivative. Okay? All right. So any questions so far? I know this is a different thing. The derivative is not a hard thing to do. Unfortunately, in the world of calculus, they will make it complex, meaning saying, hey, plug x plus h in for all your x's. Subtract your function. Divide everything by h. That's what they will originally start you with. And it becomes maddening because it's just a whole bunch of algebra you're doing with x's and h's. Okay? So, the sum rule is this. Let's say I had this. Okay? The sum rule means this. If I wanted to find the derivative, it's going to be 3x squared plus 14x to the 6th, and then that just gives me 0. You see what I did? Did I bring the exponent, like I said, down front and reduce the exponent by 1 here? I think I did. Did I bring the exponent down? Yeah, but there was 2 there, so I multiplied by 2 times 7, I got 14. And I reduced it by 1. And then the derivative of a constant is just 0. So the derivative of this is this. Okay? So the sum rule just basically means we're adding things together. The difference rule means this. Let's take the exact same equation. Okay, the only thing I changed was this. So this is going to be 3x squared, so dy. Thank you. This is going to give me minus 14x to the 6th. The only big difference between the two is one has an addition sign and one has a subtraction sign. That's the big thing about the two. Extra one and print something. Bless you. Sorry about that. Okay. Good so far? All right. So now let's go down to derivative type questions. Write the equation of the line tangent to f of x equals root 16 at 16. Huh. First off, is this a constant? So the derivative, we're going to use f prime. This means I took the derivative. Is equal to 0. So can I plug, is there any x that I can plug in here? No. So this is going to be 0. They could have given me something better. So write the equation of the line tangent to that. That's kind of goofy. That's our equation, 0. But if we have this one, and they want to know at x equals 1, x equals 2, x equals -3. Okay, remember I'm going to use the little prime thing. If I do f prime at x, that means I'm taking the derivative, okay? What's the derivative of x squared? What's the derivative of this? 2x. Okay, so now, that's the derivative. If I want to know what the slope is at each of these points, I'm going to take 1 and plug it in. I'm going to take 2 and plug it in. And I'm going to take -3 and plug it in. So the slope at 1 is 2. The slope at 2 is 4. Okay, these could be fractions, so 4 over 1 or 2 over 1. And the slope here is -6. Okay, that's all you're doing. Okay, so what that means is if I had graphed x squared, let's do this. Let's set Desmos. I have x squared, and I have 1 with a slope of 2, 2 with a slope of 4, and I have -3 with a slope of -6. Okay, so jump to our buddy Desmos. Okay, we have a parabola. Okay, let's zoom in a little bit. There we go. Get a little darker. Okay, so if I come to 1, oh, I want to let 1 to show up there. If I get right here to 1 and I come straight up, if I did my math right, this ruler is representing a tangent line. So the slope exactly at this tangent line, exactly where it touches there, right at 1 in the x, this will have a slope of 2. Meaning if I found the equation of this line, I would have to go up to right 1 in order to keep generating it. If I went to 2 is, we have to, okay, notice I have a 2 down here. So if I came right up here, this has a little bit different slope. The slope right there is going to be 4. And if I were to go over to -3, so notice we have the -3 right here. If I come straight up and I make this line tangent just like this, Should be a negative slope because it's a negative line. So it has a slope of -6, meaning I go down 6, right 1 for that equation of that line. That's the definition of a derivative. Okay? Derivative allows you to then find the instantaneous slope, a singleton point of the line tangent to our equation. Okay? And this is a little different. I don't want you panicking on this. I can get you through it. It's not something that's a horrific thing. Let me try and do this. So letter A, if I have f at x equals 7x minus 4, I'm going to say f prime at x. That means I'm taking the derivative. What's the derivative of 7x? 7. What's the derivative of -4? 0. So my derivative of this equation is just 7. For letter B, if I had this, I'm going to take the derivative, so f prime at x. What's the derivative of x to the third? Close. 3x squared. 3x squared minus, what's the derivative of this? -4x. Good. So minus 4x is because of the negatives in there. And then what's the derivative of 10x? No. How much? 10. Yeah. Okay. And then letter C has a little bit of a curveball in it. And then we just have to kind of take our understanding of what exponents do. Okay. So if you have a variable in the denominator, we can move it to the numerator by changing the exponent from a positive to a negative. So if we change locations, I'm not taking the derivative yet. I'm going to write this. Which this cleans up to this. Okay, so what did I do? I moved our term, our variable, out of the denominator. I moved it up. By me moving it out of the denominator or to the numerator, I moved it from bottom to top, or I moved it from top to bottom, the sign on the exponent has to change. If this was already a -5 and I had moved it up, x to the -5, and I moved it up, it'd be x to the 5th. So the sign changes. So now, ready? Are we okay so far with that? Can you kind of follow what that's doing? All right, I want to take the derivative, f prime at x. So it's going to be -5x. Now we have to be careful. We were subtracting 1 from the exponent. What is -5 minus 1? -6. Good. And then bring down that 4. 4 times -2 is going to be +8. X. If I subtract 1 from -4, what do I get to? -5. Okay? You just did the derivative of something pretty darn complex. Okay? So, let's have us do this. We're going to go to worksheet 4.3, but I'm only going to give you a couple problems. Let's have us do 4, 5, 6, and 7. I just want you to try the derivatives. For number 7, you have something that looks like this. We have to know that this is the same thing as x raised to the 1/3 power. So this has to go with number 7. So just try those 4. I'm giving you a tiny, tiny, tiny amount of homework to do. I just wanted you to focus on trying to find the derivative of each. And that's all I have for you. Sound good?